Discuss about jump and call instructions in this session. So jump are the instruction which will make a jump to a particular location based on certain condition. For example, you can look into the first instruction which is saying JZ, nothing but jump if 0. So this instruction is used to check out the contents present in A. If the content present in A is equal to 0, then it will make a jump to a location. If not, it will execute the next set of instructions. So these are the conditional jump instructions like jump if 0, jump if not 0, decrement and jump if not 0, compare and jump if not equal with the data which is present in register and the immediate data what we are using, jump if carry, jump if no carry, right? So like this we have the different conditional jump instructions. We'll take out the first one, that is jump if 0, nothing but if we are using this instruction when the content of A is equal to 0. So look at this set of instruction. Here we are trying to move the content which is present in R0 to A. Now check out the content which is present in A. If A is equal to 0, then go to the location over. Jump if 0 over. So you have the location over here. Similarly, we will go with the next set of instruction. Right, if it is not 0, then you can go with move A comma R1, where again you are trying the content present in R1 to A. Check out whether A is equal to 0. If it is 0, then again move to the location over. So this jump Z, what we are using, jump if 0, is the instruction which is used to check out only the content of accumulator, nothing but the content of register A will be checked. For that checking of that condition, we will be using this jump if 0 instruction. So we will go with an example which is used to determine what are the content present in R0. If the content present in R0 is FFH, then we will be moving that FFH to R5. We will be moving that FFH to R5. So now you can see here we are loading the content present in R0 to A. Now we have to check out whether the content in R0 is FF or not. So what you will do, you will move that content to A, then you will say increment A. So when you are saying increment A, if the value present in FF, A is FF, if the value present in A is FF, when it is incremented, then the value will become 0. If it is 0, then you will execute this instruction, that is moving FFH to R5. If it is not 0, then you will move to the location next. So you will check out whether the content present are FF, just send the data to A, increment it. When it is incremented, it will get 0. If it is FF, then it will become 0. If it is 0, then you can execute this instruction. If it is not 0, then you can jump to the location next. The next one, that is jump if no carry, that is if carry is equal to 0. So this instruction will be executed. Check out for the condition. If the instruction is correct, if the condition is correct, then you will jump to the location. If not, you will execute the next set of instructions. So these jump what we have discussed, they all are conditional jumps, and the conditional jumps what we are using, they all are short jumps. We say the short jumps is nothing but the address of the target will be in the range minus 128 to plus 127 bytes of the contents of the PC. When we are using conditional jumps, these conditional jumps are short jumps. They will be having the range between minus 128 to plus 127. So next we will move with unconditional jumps. So unconditional jumps, there are two kinds. One is L jump and the other one is S jump, nothing but long jump and short jump. So when we are moving with long jump, so this long jump is a 3-byte instruction. In that, the first byte will be used for opcode, and the next second and third byte will be representing the address of the target location. When we are using this 2-byte this 2-byte of address, it will allow us to jump between 0002 to FFFFH. Right. So we know the 8051 microcontroller have 64 kilobytes of on RAM. So where all the 8051 family members does not have this 64k byte of RAM. For example, the original 8051 had only 4 kilobytes of RAM. So when we are saying L jump, nothing but long jump, so here we will be using 2 bytes of address for the target. So the target where your jump is present, and which is can be accessed between 0002 to FFF, where based on this program memory, where it will be it read less than 64k, we can go for the next kind of jump, that is short jump. So this short jump is a 2-byte instruction where the first byte will be opcode and the next byte, what we have the second byte, it will be used for your target accessing. So with the 1 byte you can have the memory location between 00 to FFH. This memory is divided into forward and backward jump between -128 to +127. So if the jump is forward, the target can be within the space of +127 bytes from the current PC. If the jump is backward, then the target address can be within the space of -128 from the current PC. So when we go with L jump, that is long jump and short jump, they are the unconditional jump. So L jump is a 3-byte instruction where the first byte will be giving you the opcode and the next, second and third byte will represent the address of the target location. With L jump, you can have the target accessing location between 0002 FFH, and we can access all the target which is in the range of 64k byte. Whereas not all the 8051 family members do have 64k bytes of memory, program memory. So we'll go for the next kind of jump, that is short jump, which is a 2-byte instruction where the first byte is for your opcode and the next byte is used to access the target. So which is like the memory is between, the location is between 002 FFH, which is divided into forward and backward between -128 to +127. Let's move with call instruction. So this call instruction is generally used when we are using subroutines. So subroutines are nothing but the subbed task which need to be executed repeatedly on different values. For example, we have written a program where a set of instructions need to be executed repeatedly on different values. So instead of writing those instructions repeatedly, what we will do is we will write a small program which is executing the same task and it will be saved in the memory. That subtask will be saved in the memory. Whenever it is needed, we will make a call from main program to that subprogram. We will go over there, we will execute that subtask and we will come back to the main program and we will continue our execution. So here when we say subroutine is nothing but a subtask which is also stored in memory. So here when we are moving from main program to subprogram, that is we call it as calling program and subroutine. So this is your calling program and this is your subroutine. In this calling program, you will execute an instruction which is called as call EC. So this call EC is nothing but this is the name of the subroutine we are using, which means that we have to go to that subtask so that we can execute that, and after the execution we have to come back to the main program. So whenever we are calling a subroutine, it is associated with an instruction called as call instruction. Once this execution is over, we have to come back to the main program. Therefore, this is associated with one more instruction. We call it as return instruction, nothing but RET. Right? So when we are saying RET, it means we have to return to the main program, nothing but your calling program. Once we are returning to the calling program, now we have to continue our execution. So now the question is from where we have to continue, whether we have to execute the first instruction or we have to execute the instruction which is after this call. Now we have to execute the instruction after this subroutine is executed, the instruction which is soon after the call. Right, now the question is, how do the processor knows from where it has to resume the instruction? Therefore, whenever we are moving to the subroutine, when we are calling a subroutine and we are moving there, we have to save the content, that is the address of the instruction after this call, address of the instruction after this call on stack, so that once this subroutine is executed, we can return over to the main program and continue our execution. Therefore, the subroutine what we are using, it will be associated with two instructions. One is call and the return. When we are saying call, it makes a jump or it makes a switching from main program to the subprogram. Once subroutine is executed, it will say return. Return is nothing but return to the main program. So when we are moving and we are coming back, before that we have to save the contents of the address, right? Contents nothing but the address of that instruction from where we have to continue our execution, that will be stored on stack. So when we are using this stack, definitely we go with the two set of instruction. One is push and the other one is pop. So push is to save the content before you move the subroutine, and pop is to return to the main program once your subroutine is executed. We go with call. So there are two kind. One is L call and the other one is A call. So L call is nothing but long call. So this long call is the 3 bytes of instruction, where the first 2 byte is your opcode and the next 2 bytes is to say about the address of your target, nothing but where your subroutine is stored. So with this L call, you can have your subroutine to be stored in 64k bytes of memory. So in this given range, your subroutines will be there. Whenever you are calling, you can switch to your subroutine which is stored in this memory location. The second set of call is A call, nothing but absolute call. A call, nothing but absolute call. So this absolute call is 2 byte, where the first byte is your opcode and the next byte is to say about your address of your subroutine, nothing but your target. So here the memory can be accessed, nothing but your subroutine, your target can be in the range of only 2k bytes. This is about the different call instructions and jump instructions supported by 8051 microcontroller. Next we will move with rotate instruction. So making your data to be rotated either left or right. So first we will take RRA, nothing but rotate right. Rotate right. So you can rotate the bits either left or right. So first we will take with RR, nothing but rotate right. So this is the representation you have. When we are rotating, you can see. So this is your LSB bit and this is your MSB bit. We will represent it as D0 and I will say this as D7. So when we are rotating right, when we are rotating the given data to the right, the bit which is present in D0, it will be exited, right? It will be exited and it will be put back into the location of D7. So when we are rotating the bit, so the D0 bit will be coming out and all the consecutive bits will be filled and D7 bit will be vacated, right? The bit which is exiting the LSB, it will be put back into MSB. So you can see here, this is the example we have taken. We have taken 36. So now we are moving the 36 to register A. So once we are doing rotation, you can see here the D7 bit, it was 0, where it has been put to D0 bit, which is 0, it has been put it to D7. So when you are rotating right, the D0 bit will be exited and it will be put back into D7. So again we are saying rotate right. So again this will be executed. When you are executing, so D0 bit is 1 here, so that one will be put to D7. So lastly we have trying to execute RL, which is rotate left. Saying rotate left, again this is D0 and this is D7 bit. When you are rotating left, the MSB bit will be exited and it will be put back into LSB bit. So you can see the example over here. We have taken 72. You have done the first rotation. Once you have done the first rotation, the D7 bit what you had, it has been put into D0 bit. Like this you can execute rotate right or rotate left. We have the next set of rotate instruction, that is rotating through the carry either left or right. That is, in the previous case the D7 bit or D0 bit, it was supposed to be exit and it has been put into the other case, right? So here we have carry also included here. So when you are doing rotate right, the LSB bit will be put into carry and the carry bit will be put into MSB. Whereas in the previous case, when we are saying rotate right, the LSB bit, it will be exited and it will be put back into MSB. When we are saying rotate through carry, the LSB bit will be put into carry and carry bit will be put into MSB. So you can see here, initially you will be taking carry is equal to 0. So once we are saying RRCA, the carry bit will be put into MSB and LSB bit will be putting into carry. So this is rotating through the carry, this is for rotating right. RLC, that is rotating left. You can see here you are rotating the information present in the register. This is D0 and this is D7. The D7 bit is exited and it is put into the carry, and the data which is present in carry has been put into LSB. MSB to carry and carry to LSB, and this is the example we have taken. Lastly, we have swap instruction. So this instruction, it was only on the accumulator. It will be just swapping the lower nibble data with higher nibble data. You can see here. So this is the general syntax we have. So this is your lower nibble data and this is your higher order information. After swapping, so D7 to D4, it will be stored in lower nibble, and D3 to D0, it will be stored in higher byte information. So this is the example we have taken.